welcome speech. A fast welcome speech for our workshop today, and the topics which will be covered through this workshop. Also, there will be different sessions. We will go through them quickly because we don't have a long time to announce each speaker. So each speaker will begin a brief announcement for himself while presenting himself. The workshop today, as been announced before, is for the project which is funded from the SDGF and mutually between the German funding agency, the Adhesive. Also, we will have a brief for the activities in the project. We will have a brief presentations from the team members discussing the different items for the project. Firstly, the project is dealing with the developments for the RO membranes. So in our first section or our first presentation, we will outline the problems which facing the RO membranes in Egypt as a country which nowadays needs the desalination and feels the severity of the condition now for the water. I want to say the water scarcity. So we will outline this in our presentations. Also, we'll go through the defects which faces the RO spreading in our country. Also, we'll discuss and express the role played by the German partnership in this project. And how the collaboration enhances or increases the development of the development process. Okay, we can now begin with the presentation. The first presentation. I now begin. Just a moment. I'm trying to share the screen now. We are now sharing the screen. I hope all of our participants is seeing it now clearly. Now we will begin the first presentation in our workshop. As you can see, the title for our presentation will be RO membrane surface modifications for water desalination. As I begin in my a few minutes welcome in this day, I have talked about the surface modifications and how to modify the current status of the RO membranes to be suitable for spreading the desalination technology to reach all of our requirements in the Egyptian markets. Yeah, this project is mutual project between the German and the Egyptian institutions. From my side, my name is Marwa Shalabi. I am a professor in the chemical engineering department and a member in the flat sheet membrane group in the National Research Center, presenting the Egyptian partnership here, and have my partner with Professor Ralph Wolken, which is a doctor in the German institution Fraunhofer for Material and Surface Modification Center. Today we will have a talk from the Egyptian side, and so some talks from the Egyptian side and other talk with the German side. From the Egyptian side, I'll begin my presentation today with the contents of our presentation of this day presentation will be the background for then the current situation and the problems with RO membranes, the previous achievements towards solution, and how is coming with a suggested solution, the experimental work, results and discussion, and also the future perspectives. If we are going to see here, you can have a look for this presentation, where the first situation which will be outlined today is the water shortage problem, which is now clear, where if we look at from the beginning, that we have many resources for the salt water. Around 97% of the water covering our earth is salt water, and also only the fresh water covers 2.5%, which is the lakes and rivers, groundwater, some of the swamp water and others. If we are looking about the concentration of desalination water, it was coming over 5,000 milligrams per liter. Here we can have a look for the situation for the water shortage in Egypt. If we can see here the situation which changed drastically or dramatically since 1955, where the share or the per capita of the water per meter cube per capita was around 2,560 and decreases to reach today to be around 500 meter cube per capita. If we can see the coverage for these resources in Egypt, we can see only the groundwater 11%, the surface water 88%, and now the desalination is sharing with only 0.6%. But with the great increase in population in Egypt, and also the scarcity, or I want to say the increase in population and the stabilized amount of resources from the surface water, 88%. This means that we need to get more and more water from desalination. To see the current situation and the problems with the membrane desalination, we can see the first emerging problem will be the fouling. The chemical load with the fouling, which leads to increased chemical cleaning processing, which gives a high chemical load for the environment. Also, you can see here in the photo for the fouled membrane, which is as you can see, blackened, which is a type of biofouling, which is dealing hard with the sheaths of the membranes. So increases the load of the chemical use, which is done nowadays, that more or less different membranes, which found from international companies all over the world, comes to Egypt and now is used on ground. So this means that we have a high chemical load to be discharged with wastewater, increasing or stressing on the problems with the desalination, not only for the drying problems, also we have the wastewater with the cleaning technology. So in our thoughts, when we are thinking about solving this problem, we are thinking about how to get the problem from the source, how to solve the problem from the source, how to solve the different types of fouling, how to go through it, how to decrease the needs for chemical cleaning. This is also another situation which seems to be a very hard one, is the increasing cost for the RO modules. The RO modules for us in Egypt now, as I said before, is 71. So we are depending on the large cost for the RO modules. By losing these modules, as you get these modules from the manufacturing, they are from the manufacturing company. They are saying that these modules can stay working from 7 to 10 years. This was get in the safety data sheet for these membranes. But on reality, by application of these membranes, we can lose the membranes by 2 or 3 years. This also may be a great drawback for the fouling, that we are using different hard techniques for the washing techniques, which go through the layers for the membranes, make some scratches, make some deformation for the polyamide layer, and decreases the efficiency for the membrane day by day, till losing all the sheets for the membrane, and the membrane goes to failure. As you can see from the middle photo, it's a scales, hard scales of fouling salts, inorganic salts, also some scales of iron, some scales of waste, which is deposited on the spiral wound sheets for the membranes. Okay. On the other hand, we can see another important problem, which is the chlorine exposure problems. Because as you can see here in our waste desalination plants, using the RO membranes, you can see that we are pre-treating the water. One of the main steps for the pre-treatment is the disinfection. The disinfecting agents, one of the important one which is used is a chlorine. One can say why we are using chlorine to disinfect before RO modules, because we need to get some pre-treatment stages before using RO. So when we are using these pre-treatment stages, if we are not using some of disinfection or some of how to kill the microorganism, how to kill the sources for the algal or bacterial growth, it increases more and more and will clog the pre-treatment stages. So we need to have some of these stages having some chlorine doses, which decreases the load for the feed water, which go through the pre-treatment, and make the using of it more easy to be used. And so this will facilitate the, I want to say, the ease of working and the ease of sustainability of the system with the decrease of the evolving problems. I want to say that the using of chlorine or some of the agents, chlorine oxide as chlorine gas, whatever the type or the hypochlorite, some desalination plants are using something like this. Whatever the source, we need to have to get rid of this chlorine. The main target of the chlorine is to get such a pre-treatment stage and then get rid of the chlorine. But still, we have some traces which go through the polyamide membranes. We want to say here that if we have only 1 ppm, means 1 milligram per liter, for chlorine goes through the polyamide layer for the RO membrane, it causes some destroying for this layer. We can see that chlorination plays an important role in the amine group, which is the main functional group used for the polyamide, which play the main role in the separation of the monovalence and the salts from the feed water, from the seawater, from the brackish water, and get its permeate water free of salts. So this layer, which is a very, very sensitive layer, this sensitive layer can go through broke down, weakened hydrogen bonds, and so the nitrogen bondings will be destroyed through hydrolysis, which made by chlorine, and is very, very favorable to be done by increasing the pH. This means that the membrane will lose its advantage or its active layer and begins to lose its properties, or I want to say not properties, the membrane will lose its activity. Okay. So what's going on? We are working in this field since many years ago. So we are a group working towards this, how to get a solution for get a sustainable RO membrane production process. We are going through the whole production. So one of the main defects which was found, as I said before, is the chlorine, is the fouling, chlorine exposure is the fouling, and with its different types. So one of our studies which have done before is how to utilize the graphene oxide and the zinc oxide nanorods and nanospheres in the enhancement of the RO membrane. If you can see this, figure, we can have a look here for the effect of this formulation of graphene oxide, zinc oxide on the contact angle of the prepared membrane. But these membranes were prepared by using the traditional way. What's meant by the traditional way? That these nanoparticles were embedded not in the membrane matrix, but it was embedded in the thin film composite, which is still a very sensitive layer. Sensitive layer, I want to say that it loses its activity after a certain chemical treatments, prolonged chemical treatments. So this study was going through how to modify the thin film composite layer. So these nanostructures were added to the aqueous layer for the thin film composite. Here you can see also a structure, a scanning electron microscope micrographs for the thin film nanocomposite RO membranes for the sections from on the right from AB, which is found for the percentage for the graphene oxide, 0.01%, and we can find the DH with the percentage of 0.02% for the graphene oxide, and in the samples, in the two other samples, we can find the structure with increased percentage to find it 0.03 weight% for the membranes. The structure is being here changed as compared with the Persine membranes, which is found at A and E, which is the first one. The photo here is getting the top section, the top surface, and the E plot, which is the cross section of the membrane. Here you can find the active layer, which is changed a lot by the absence of the graphene, and then the addition of a certain concentration of graphene oxide and zinc oxide nanospheres and nanorods, which is optimized through this study. The composition or the change in the active layer and its structure as shown in the SEM charts is highly here presented or highly shown in the water flux and the percentage rejection, which was highly illustrated in these figures. We can see here the membranes which containing only graphene oxide in black, the others colored ones having the change between the same concentration of graphene oxide, zinc oxide, but with the change of the morphology of the zinc oxide nanostructure, between the change between the spheres, flowers, and rods. When we are doing the structure of the zinc oxide in spheres, which is found in red, which found to be the best for the water flux. And also when we have here go through the percentage rejection, you can see here the blue one, which is the structure with the flowers. Also, we can here see when, as we go through the comparison with the published literature and the found percentage salt rejection, we can found here that in our study, by increasing the percentage between the zinc oxide and the zinc oxide nanospheres and the graphene oxide, 0.03% by weight, we can find here a great enhancement of salt rejection to reach about 100%. All means all the salts found in the water was rejected and the water was coming out free of salts. This is when compared, for example, by using the graphene oxide alone, by embedding the graphene oxide alone, we don't have a high percentage of rejection, the difference in rejection as it was recorded in the literature to be 99.4. Also, if we can see the commercial ones, the membranes which is produced by Dow, brackish water membranes, brackish water 30, we can find it to reach also 98.6. Okay. Okay. Also, the target or the aim of this work was how to see the effect of the fouling while using a fouling solution composed of humic acid, calcium chloride, and in presence also of sodium chloride. Here's the four types of the membranes: the pristine membrane, which is free of anything, which is the commercial, presenting the commercial one, which we have also been prepared by our team, which have no additions when compared to the one which with the percentage of the zinc oxide, nanospheres, nanoflowers, and nanorods. We have here gone to a compaction period, which about 3 hours. We got the membranes to go through the compaction period to be away from any salts, away from any additives, which was going through the preparation for the membrane. We can see here the variation in the behavior of the fouling behavior while using the same solution or the same fouling solution, that the pristine membrane show a high decline or a variation in the normalized water flux to decrease dramatically from 1 as the flux when normalized between the instantaneous flux and the flux at the beginning. So it decreases from 1 to reach around 0.4, which is a great decline in the flux. Means the membrane loses more than 60% of its activity to produce permeate water. While when we are comparing the others with the pristine with the 0.02 zinc oxide nanospheres, which is the optimum one for the flux production, we can see only loss in the flux to be only 0.9. From 1, it decreases to reach only 0.9. Also, this was reflecting on the perfect structure which we have reached to a a high percentage of roughness, lower surface was attributed to the decreased adhesion of the charge, which is negatively charged, was having some stability for the brackish water pH. Okay. Now we will go to another solution, which is was done by our group, how to study the effect of fouling control by means of ultrasonic frequency. This work was done to highlight the role played by the ultrasound waves, how the change in the ultrasound frequency will enhance the mechanical forces or have some cavitation, which it's very useful for getting a powerful fouling behavior or a powerful anti-fouling behavior. If we are going to highlight this technology, we are using, as you can see in the drawing in front of you, that we have a bath, and this bath containing 2 ultrasonic transducers, which is giving ultrasonic frequency, which is with a variable frequency. We have tried in this work, we have tried 2 frequencies, 35 kilohertz and 130 kilohertz. 35 is denoting the low, and 130 denoting the medium-high ultrasonic frequency. So if we are going through this, we can see that the maximum electric power, which was found in the bath where the membrane was found in this bath to take some treatments with this ultrasound. So after this, we can find here a change in the membrane flux. We can find that the fouling rate with the membrane alone and the as measured for the transmembrane pressure, we can find the transmembrane pressure with the time of operation. We can find the membrane alone without any ultrasound treatment was the worst, and also the higher frequency of 130 kilohertz also was not showing a good work. The best work was found with the treatment of the membranes with ultrasound 130 kilohertz for the frequency. The percentage reduction for the ultrasound 130 was around 15%, 36% for the 35 ultrasound, 35 kilohertz, and the percentage reduction for the 130 was 15%. But this was the lowest flux which is given, and the percentage in the combined process. This was due to the higher cross-flow velocity and the higher shear-induced hydrodynamic forces, where the particles were detached with the membrane surface by the shearing action and of the cavitation mechanism, which is carried away from the membrane surface and increases the feed flow and increase the flow through the membranes by action of this ultrasound. Okay. We can go another experiment or another work, which is going through or towards the solution of the membrane problems. One of the important problems which was found to have a great impact on the behavior of the membrane is the support. All of us know that when we are going or seeing the spiral wound modules from inside, we can see that the membranes are not casted by itself. No, it have a type of fabric support. This fabric support is highly influencing the properties of these membranes. So if you are go through the effect of the structure of this support, we have in this study, we have go through this comparison where we are comparing the woven structure, the non-woven structure, when compared to the unsupported membranes, which I mean that the membranes were casted on glass plate. But in other words, we can't use the membranes which is casted on the glass plates for getting spiral wound industrial modules. As I said before, our group is devoted and going through a target where how to serve the Egyptian market, how to go to the population which needs water. So we are getting our work to how to be translated to go through the Egyptian market, to go to and serve the research to serve the community. This is our target in our membrane group, flat sheet membrane group, where we are working since many years ago. And so, if you here have a look for this study, you can see that we highlight here the impact of using different type of support on the structure of the prepared asymmetric membranes. As you can see here, we are getting a certain structure, a certain composition for the membrane using polyether sulfone, which is fabricated by phase inversion and used here a casting solution by 6% nanomaterials solution and this nanomaterial solution is added in addition to SDS and triethylamine in presence of titanium dioxide to enhance the anti-fouling behavior of these RO membranes. So we have here, you can see clearly that the prepared membranes, which was casted for the M1, which is the membrane when casted over the glass without any support. M2 is the non-woven, where we cast the membranes over a non-woven fabric support, which have a certain characterization. Then we can see 3, which is the woven support. The woven support have the structure here. You can see in the scanning electron microscope morphology, which is clear to have a neat layer, thin film layer for these membranes. Also, you can see here the change in the porosity, that while we are casting on a glass plate, we get 35.7 porosity, which increases to be around 40 and having a mean pore diameter of 8 when compared to the unsupported one, which is only 6.5. Okay. A great enhancement was found with the compacted woven support when using the fouling experiment. While using here, we are using woven serum. And this one, we have seen clearly the membrane, which is in red, which is the treated membranes with which is the TFC membrane, which is the commercial one. And when compared to our membrane, which is M3, which is the woven supported prepared RO membrane in presence of titanium dioxide. Here you can see the effect of the presence of a supported material and having also enhancement with the great enhancement with the flux to reach around 134.9 kilogram per meter square hour. Okay. Then, as I said before, our goal was how to get large-scale application. This is one of our goal targets in our projects, in our research work, and in our applications, how to scale up, how to scale all of our achievements which have been presented this day was lab scale achievements, but we have the facilities in our group how to enlarge the scale, how to go through large scale RO membranes using continuous membrane casting machines, using the production of spiral wound modules, as you can see here. Also, you can see the way for getting these modules. This is real photos from our laboratory, and this we have a simple testing machine for this one. Then we can go fastly, because I think time is gone. I'm sorry. Go fastly through how to suggest a solution, how to get a solution. Nowadays, after getting all these achievements on real, we want to talk that some of these achievements nowadays is not going to the industry. So still up till now, we can get the RO modules, which can't bear the chlorine exposure, can't bear the foulants, which can be found and may change in the desalination site. Meanwhile, after getting designed and implemented, so we need to tailor a membrane. RO module getting membrane sheets which have these protection or defense ways to defend the membranes and the module from running away. Okay, so our suggested solution to synthesize or get some surface coatings which get a low-cost membrane. This is one of the goals of our project, a low-cost membrane which is composed of some materials, developing of these nanomaterials, zeolites, titanium dioxide, carbon nanotubes, graphene oxide complexed with any other way. The getting benefits of the chemical grafting to increase the the chemical grafting to increase the contact between the graphene oxide and how to get benefit from this graphene oxide. Why graphene oxide? Why we are stressing on graphene oxide? Also, I have, or my group, me and my group have previous publications in graphene oxide. But now we are trying to have a new look for the graphene. Why? Because the graphene, as I said before, was only embedded in the aqueous solution or the aqueous layer for being cross-linked by the organic layer forming the TFC membranes. So we are now trying to have another look, another way for getting benefit of this graphene. Why graphene? Because graphene is very, very powerful in absorbing chlorine radicals. But to absorb the chlorine radical, the graphene needs to have some linkage, some cross-linking, some functionalization in the surface of the membrane, and how to get the suppression, how to get good chlorine resistance in suppressing the degradation of the salt rejection. Because as we go through getting the chlorine resistance high, we can lose some of the salt rejection. So this is one of our goals. The other goal which we are targeting in this study, the spacer geometry, the spacer treatment, the spacer pre-treatment, because it plays an important role when we are targeting spiral wound modules. Because when we are targeting spiral wound modules, not lab scale flat sheet membranes, we are targeting, we are getting through the spacer geometry. The spacer geometry have many publications going through 3D printing and how to tailor, how to change the angles, how to change the tilting of these spacers, something like this. How to get use of the electromagnetic field, how to get use of the plasma waves, how to get use of the ultrasonic waves, as we said before, on the spiral wound modules, how to get benefit of the ultraviolet, how to get benefit of some types of treatments for the surface treatments of the sheets of the membranes, which increases its chlorine resistivity, increases its anti-fouling behavior without getting through the flux change, because we need all time to enhance the productivity of these membranes. Also, we need to have a higher percentage of rejection. Sorry. So, another key factor for our study today was the application of tannic acid. Why tannic acid? Because tannic acid is a green additive, is a green monomer. It comes from green technology. So, if we are going through this old literature, we can find that tannic acid has an old name, which is known as chemeri. And this tannic acid, which is found from some type of green leaves, when embedded through the interfacial polymerization, was achieving a higher percentage of rejection. But in our study, we are trying to tailor the different properties or different studies for the membranes applying the tannic acid. In our experimental work, we are devoted to the presence of the zinc glycerolate, the presence of graphene oxide coupled with zirconium dioxide and silicon dioxide, and how to get these nanostructures embedded in the membrane preparation, embedded in the thin film composite, and also in the other layer by layer deposition, because we believe that the thin film composite alone will not be able to face all the aforementioned problems. So we need to have some mixed, some deposited layers by the technique of the layer by layer to get rid of some of these problems and get the membranes to be more and more. Here you can find some illustrations for the chemical bonding, which can be found by an example of the chemical grafting, which is done over the thin film composite, and how the use of the chemical grafting and the use of some cross-linking over the membrane surface will enhance a lot its applicability in terms of flux and salt rejection. Also, the presence of polyvinyl alcohol and how to get benefit of this polymer is here being illustrated. The presence of different structure, as you can see here in this diagram, will show the grooves for the permeate flow, the effect of the assembly for the testing structure for the membrane will play an important role for studying the performance, measuring the performance of the membrane, and measuring also the fouling experiments. Here in our study, we are using a polysaccharide foulant, which is sodium alginate, coupled with other organic and inorganic foulants. This is a part of our lab equipments, which are used for the presentation, for the performance, measuring the performance and the casting for the membranes. Here clearly, also the increase in the percentage rejection by the effect of the blending technique and the thin film composite. Finally, I want to get how to compare our studies with the plasma treatments, the vacuum UV, and using the continuous chemical-based surface modification, how to produce RO spiral 1 modules for continuous experimentation, how to get benefit, to get low cost water desalinated by giving a complete techno-economic pre-feasibility studies for the different study scenarios. Finally, I want to invite you all for getting through our third international conference for membrane technology and its application, which will be held next summer, and keep in touch with us to know the whole details. Finally, I want to acknowledge my group, Flat Sheet Membrane Group, MTAIC, and the Central Laboratory and the Center of Excellence in the National Research Center, the Egyptian Society for Membrane Technology and its application, ESMT. Thanks for your attention. Also, I'll be happy to get any questions. You can send it, and I'll try to send you the reply. Thank you. Yeah.
Professor Marwa.
First of all,
yeah.
First of all, I would like to. Can you hear me well?
I'm hearing you, Dr. Wael. Hello, well? You are welcome.
My voice is clear.
I think you
first of all, I'm very happy to have this wonderful.
I think we need to switch the camera to hear you because the connection is not stable.
To switch the camera off, okay.
Yeah, okay. Yeah, I want to hear you now.
Good.
Yeah.
Is it good now?
Okay. Yeah, it's good.
First of all, I'm very happy. First of all, I'm very happy to be with you today. And I'm really proud of the Egyptian woman scientist. I mean, it's a great presentation. And I was really impressed by the quality of the work and the lab, actually. The lab is a great lab. I mean, we started from the flat sheet membrane and we moved to the spiral bonding, and this is very great. I will have to, I have two questions, one for the scientist and the other for the engineer. I mean, from your presentation, you were adding some modifiers and some science of chemistry. The first question is, usually the RO membrane are composed from three main layers: the polyester, the polysulfide, and the polyamide. So your interaction is the first stage. I mean, the chemical modification or the additives that you are modifying interacted specifically with which layer. You mentioned the importance of the polyester layer, supporting layer, but actually I didn't get how you are interacting your modification at which layer and which levels and within the preparation or after preparation, is it just coating or there is a chemical interaction during the preparation. So this, I mean, maybe due to the Zoom characteristic, we couldn't follow you up. I couldn't follow you up carefully. So this is the first. Second, I will give all my question and I will leave the floor.
Okay.
The second is usually the fouling parameters is affected by two different levels: the chemistry level and the engineering level. So I mean the film casting process, the film coating process. There are many disciplined or interactive parameters that could affect the anti-fouling or fouling resistance of the membrane itself. So we have like a chemistry part and engineering part. So I couldn't understand how could you make the comparison fair for the RO membrane available in the commercial one that you brought it and to compare with yours. While I think the environment is quite different because you are working in a lab scale, and you know that the engineering at a large scale will be quite different. Third question is, I do believe that.
We do.
Okay. The third one is not a question actually. It's like
we are running away of time. I'm sorry.
Okay. Oh, alaikum salam. I will give you the last one. We have now in Egypt 3 different main groups. I mean, groups, your groups and the group of the. I think there is 2 different groups in RC. So how is the link between these groups and when we can find in the market Egypt made
options while getting the third one. Okay. For the first question, yes, we have 3 layers for the membranes, and we are trying to go through the 3 layers because the first layer, which is the support polyester, plays an important role, which is it's not easy to be you want to say to be neglected. No, it plays an important role. The middle layer for the polysulfone or the support polymeric support layer, also we have to add some modifications to play its role powerfully. For the modifications which I have presented in my work today, we are going through the first layer, which is the thin film composite layer. But for the future perspectives, which I'm going through it by the following year in my project and in other studies for our group, we are going through modification of the bottom layer and the middle layer too. This is the first question. The second question for the behavior of the fouling, the fouling behavior. Yes, the fouling behavior is not easy, but from my side, during my our previous studies, some of my colleagues have go through the chemical structure for the fouling and going through defining them well. Others go through the modeling. But while presenting now, I'm presenting the end application as an engineering application, how to get through the comparison while comparing the normalized flux and comparing the fall in the flux while getting the membrane over high duty, which is the traditional or the classical study for the fouling, not going through the transport model, not going through the studies of the main composition of the foulant and how it plays with each layer of the membranes, maybe coming or ongoing research. Thank you, Dr. Wael, and hoping to receive your more questions while chatting room. Yeah, thank you. We will present now our second presenter in this day, which is Professor Shaban, Professor Ahmed Shaban, the former Vice President of the National Research Center and is the head of our flat sheet membrane group. And he will now present he's the co-PI for our running project. So he is presenting now his view for our group and the view for the project. Yeah, thank you.
Good morning. Firstly, I would like to thank our great partner from Germany, Dr. Ralph, also my PI, Dr. Marwa Shalabi, and our great audience today. This is Ahmed Sha'ban, Professor of Water Treatment Technology, especially water microbiology. Now I am the head of flat sheet group. It's my pleasure to be the head of the flat sheet of this special group. And today I will introduce some data about this project, especially about the microbial fouling and the microbial deals with the RO membrane. All of this work was done in Center Laboratory of Network, Center Laboratory Network, and National Research Center. So, reverse osmosis membrane is relatively new membrane separation technique for size less than. This is the properties of the RO. For size less than 1 nanometer. Molecular weight is considered unknown molecular weight, especially for some manufacturing report, approximately 100. High operation pressure, RO need high operation pressure, also high rejection salts. RO, there is 3 fabrication technique: blending, coating, grafting. Blending with other polymer, with another polymer, with nanoparticle, with copolymer. Coating with interfacial polymerization, with polyamide layer. Grafting, thermal cross-linking on the surface. Those 3 techniques used for RO manufacturing. Fouling refers to irreversible precipitation, organic or inorganic material, suspended particle, or bacteria on the surface of membrane and its pores, which resulted in the decline of the water flux. So the fouling means decline or decrease in the flux. Organic or inorganic causing chemical fouling, and the bacterial and the algal and the viruses causing biofouling. The biofouling is among the most common and the most problematic types of fouling, reverse osmosis membrane. Biofouling is excessive growth of biofilm of bacteria present in the membrane, on the membrane surface. So this biofouling is meaning is the excessive growth of bacteria on the membrane. Major type of consequences: low availability rates due to chemical cleaning frequencies. So the flux became less. Needs high electricity and high chemical consumption. These are the consequences. After performance, the permeate quality and the quantity became low. Mechanical and chemical damage will happen for spiral wound membrane. So this means shortened membrane life is a money wise and economic wise. Previous work for overcome fouling, blending with another polymer. This technique was used for crystal violet removal from textile. It's clear from this figure that rejection increased with the operation time, and the flux were reduced or declined with the operation time. But this membrane was given rejection reached from 90.3 up to 97.7 for rejection, but for flux ranged from 16.5 up to 18.8 LMH liter per meter per hour. So this means that the produced flux was good and with good quality. Surface wash for membrane reuse. This membrane was used for crystal violet removal, and we wash it many times, to use up to 400 hours. From this figure, it's clear that we can obtain the maximum flux production after each washing time. Embedding with the nanoparticle, membrane based on organometallic compound showed high fouling resistance, reversible resistance depending on the format of flocculant or foulant cake. It can be removed by surface or backwash. Irreversible resistant means the pores were clogged by foulant, and this case needs chemical. In this figure, UF3 provides lowest reversible resistance and irreversible resistance 1. Coating natural hydrophilic polymer. We coating with the hydrophilic polymer. The commercial thin film composite aromatic polyamide, reverse osmosis membrane was modified through coating a surface layer of natural polymer. The deposition of coated layer on the membrane was carried out through dip coating followed by in situ cross-linking. The results of fouling experiment with sodium alginate aqueous solution reveals that the fouling resistance of the reverse osmosis membrane could be effectively improved by coating. For that, we adapting coating on the RO membrane. Surface modification of active polyamide. This means plasma increased the active sites in the RO membrane. The RO membrane was adapted or introduced to oxygen plasma, give us more and more active site to prevent the foulant and increase the lifetime of the membrane. Significant reduction of bacterial cell attachment on modified membrane surface, berm selectivity under cross-flow condition comparable to virgin membrane. Membrane biofouling test. We prepared our membrane, we submerged our membrane in bacterial supernatant or bacterial E. coli in nutrient broth. And every day we expose our membrane after bacterial growth for ultraviolet lamp for 4 hours per day. And after these 4 hours, incubated for the next day at 37 degrees. And then every day we test the membrane for testing the cell for desalination and for foulant. So from this experiment, the cultivation was conducted for 2 days. After cultivation, each day, membrane desalination performance was measured for the fouled membrane, and the membrane degradation was judged for attenuation of membrane desalination performance. We found that a good result for preventing biofouling on the membrane. Also, we test the biofouling also by the optical density. We tested by sensitivity and the optical density. From this table, it's clear that the difference between the unmodified and the modified, there is a little bit difference. The membrane composition not resistant but not support growth of bacterial strain. The modified membranes cannot support the biofouling of the membrane. From both experiments, we conclude that our membrane not support or cannot support the biofouling, especially with surface treatment. From this, we can conclude that membrane offer a wide range of applications. Membrane is a mature technology. Successful membrane, depending on control membrane fouling, coating with hydrophilic polymer enhance the biofouling resistant. The grafting surface acquire the membrane anti-fouling properties. Thank you. Before any question, I have a second presentation or second little bit information about the previous work. Sorry for latency. Actually, the present work about the removal of dyes from wastewater or industrial wastewater. So this is a type of pigment used in the textile and they produced COD and BOD and color and toxicity from the main pigment or dyes used for textile application. For dyes removal, there is a biological treatment, and we have colleagues in the National Research Center deal with this application, and he has a good result. Also, precipitation, coagulation, flocculation, flotation by traditional methods. Also, there is oxidation and absorption on the materials. In addition to membrane technology, we will deal with the membrane technology in removal of dyes. Membrane technology, there is a lot of applications like MBR, membrane bioreactor, ultrafiltration, and nanofiltration. I'll speak today about the nanofiltration dye for divalent and trivalent salts removal, in addition to dye removal. We applicated with the ultrafiltration, but we found that nanofiltration more efficient in this application with the textile wastewater. Membrane technology, we prepared membrane using textile support to provide high mechanical properties to polymeric membrane fabric support should be polyester and polypropylene, especially with woven and non-woven. And this is the electron microscopic scanning electron microscope for different for prepared membrane. We compared between the woven and the non-woven, and without support completely, we found that the woven give us the more productivity than the non-woven, and both of them more than the without support. This we used a flat sheet for ultrafiltration. Ultrafiltration, the support improve the mechanical properties and improve the permeate flux. And we compared to membrane support 100, here about 130. and here 200 or 300 almost LMH. So this means that the woven support give us flux with high rate reach the national or international flux rate per square meter. For RO, what we deal with RO, normally we use it without support and with non-woven and woven. The same conclusion we get it in the ultrafiltration, we get it also in reverse osmosis membrane, that the RO with woven support give us the flux with almost 140 LMH per hour. This means, and this best flux we get it, and we compare it with the international limits, is a good limits and almost equal to the international limit. When we applicate the membrane nanofiltration membrane BVA with CA for removal of dye, I think you have seen this figure in the previous work, on the previous presentation, but this I put it here again to show you that the removal of crystal violet from the industrial waste reach 99%. Also the washing. Fabrication of, we start to put a pilot study for, because we already did a pilot for to remove the crystal violet from the waste, industrial wastewater. We fabricate large scale flat sheet membrane. Also, we fabricate spiral wound module, and we have the know-how to be spiral. Not everybody knows the spiral wound know-how. In installation of the pilot system, when you install the pilot system, we have a long-term experiment. We have also did a back and surface wash for the membrane. We will move from small scale up to large scale. To scale up for pilot, we have casting machine and also washing machine to produce the big size, large scale flat sheet before going to be spiral. So we start from A4 up to 1 meter width, which is long up to 100 meter, flat sheet membrane for ultrafiltration, nanofiltration, RO, whatever type of membrane we do it. Also, this machine use it for rolling and fabricated the flat sheet. Cutting machine, fiber machine, and after this, we can have the module, like the modules used in the desalination plant or purification plant use membrane. Actually, we produce 40-40 and 40-20 membrane, 4-inch in 1 meter length, and 4-inch 50 centimeter inch, 50 centimeter length. There is there is a video here, but I missed it to I didn't applicate it on the, because on the lab there is no video, application video. This video show that the way industrial waste for crystal violet produce free water. When we analyzed, we can't find crystal violet in the produced water. So, and the productivity was high. I am sorry for the missed videos in this area. This is the produced membrane for our nanofiltration spiral wound membrane 40-40-40-20 used for virus, bacteria, dyes removal. I'm not speaking about goal of the membrane group, but actually from 2014, we are working before 2014, but we constructed in 2014. From this time, we have produced microfiltration, ultrafiltration, nanofiltration, reverse osmosis with different surface modification. In addition to forward osmosis, we produce it now. This is the different type of membrane we produce. The domestic one, the most different domestic size. In addition to 40-21, in addition to 40-40, and also we prepared and we manufactured 80-40, for which one will use in the desalination or treatment plant used membrane actually. We have applied our produced membrane in the field. Like in Novaria, we have a farm in Novaria, and we have wells, irrigation wells in the Novaria with desalination about 2,000 up to 3,000 ppm. We adapt our product to treat the well water or groundwater to use in irrigation by reducing the salinity and reducing the turbidity from the well itself. Also, we produce different type of ultrafiltration like PVC and the PVDF. Both of them was applied in our pilot plant in Novaria, and they produce the PVC would produce from 10 to 15 cubic meter per day, and the PVDF produce about from 7 to 10 cubic meter per day. Actually, we applicate the ultrafiltration as a tertiary treatment in Zenin, in pilot treatment plant in Zenin. This pilot produce algae. They get the biomass of algae, and the produced water still have a lot of algae and a lot of pigment, can't discharge on the stream. We applicate our system on the left side. If you see our system in the left side of the screen, this system was applied as a tertiary treatment for wastewater treatment plant. And the produced water from the this system, we analyzed in our laboratories, it almost free from bacteria, free of bacteria, not almost, free of bacteria, free of viruses. The quality of water almost, here I say almost equal the quality of drinking water. Also, there is a video, but I think I have a problem with the videos today. Product testing and for forward osmosis, we produced forward osmosis to 40-20 and 40-40. We have designed a system for treatment the tap water to be used in molecular biology experiment. So my colleague will speak about this in detail, but this show you that we produce ultrafiltration, microfiltration, and nanofiltration in addition to RO. So we produce this type. We compare it with the commercial one in the Egyptian market. and we compare the result in the application of the molecular biology laboratories. And my colleague will speak about the result. Okay. For RO spiral wound membrane, we prepared the RO membrane, and we have the know-how of the how to roll spiral wound the RO membrane, and we applicated in our laboratory, but and we applicated also in Novaria field, but not in desalination of seawater. But we have all things about the RO preparation and fabrication. All of this, we have this 3 patents, but we have 5 patents granted from our societies. This patent, we use it in our application. In addition to 6 patents was submitted to get, inshallah. Let me to thank you this photo from our laboratory to show it's real product, not a commercial one, and we can cooperate with anyone in Egypt and over the world. Especially, we have our great partner from Germany, Ralph, Dr. Ralph. I've not met him till now, but I hope we can meet soon, especially in Bremen, because I have many times in Bremen. And also, we cooperate with different societies, different institutes, different universities over the world, in China, in Poland, in Spain, in France. So we hope to increase our cooperation with the Egyptian universities, with the Egyptian institutes, with the international cooperation in everywhere over the world. Let me to thank you for listening, for attending, for everything. Thank you.
Thank you, Professor Shaban, for this nice talk. We are now introducing our great honorable participants to go through a break and begin again at 12. We will take a 20 minutes break and begin again by 12 o'clock Cairo time, which I think 11 o'clock by the German time. So we'll begin again our presentations through this fruitful workshop by 12 o'clock. Thank you for your attention. Thank you. Hello, everybody. We come back after the break. We will now we'll present. We will have in our schedule today 3 more presentations. The first one will be from Professor Mahmoud Bahgat, professor of molecular pharmaceutical and molecular biology, and he will present himself in more details while beginning in his presentation. After this, you will have a presentation from Professor Heba Abdallah, and her talk will be on the developments of the surface coatings for the RO membranes. The final presentation in our workshop will be from our partners in Germany by Christoph. After this, we'll have a simple closing words and hoping you all to have a fruitful day. Finally, I want to ask all our audience if anyone have any question which is not fulfilled in the timeline of each presenter, please try to write your question in the chatting room while putting your details via your email to get a reply through the email. Also, any of the audience which needs any other details for having some certificates for attending this workshop, please contact us on Membrane Tech 13@gmail.com. I'll put the email in the chatting room now for everyone who needs further details or any other connections with our group. You can contact us easily. Okay. Also, some of our audience have requested to see a detailed or a collective presentation summary, which will be put on the channel of the YouTube of our group. You can try to get it also by getting your email to get an allowance to go through the YouTube channel. If you will not have allowance from our administrator for the YouTube channel, you will not be able to see the review for our day. More or less, I want to thank you all for your participation and hoping you to enjoy a good day. Just some moments and Dr. Mahmoud will begin his presentation. Few minutes and the presentation will begin. Thank you.
A very good evening or good afternoon, everybody around. And one of the things that I wish to mention at the very beginning of my presentation is that I'm intruder for this meeting actually, because I am neither a membrane scientist nor a reverse osmosis scientist or a chemical engineer. However, I've been implicated in everybody of the floor needs to help an implicated person in a very hard situation. Saying that, I'm not trying to avoid working with membrane people, because without membrane people, I would say it would be very hard to live as a biotechnologist or as an infection biologist. Well, my presentation today would be how would we figure out, imagine the world during the COVID-19 without membranes. I guess this would have been impossible. And I'm not gonna try to sort of, I wanted to make my mobile silent so that I don't interrupt anybody. So I don't want to convince you, but this is reality. In the very next couple of slides, I would try to show you how membrane technology is very important to biotechnologists and to virologists. And okay. So as you all know that if you are a molecular biologist or a biotechnologist, you wouldn't be able to work in your lab without something so-called molecular biology grade sterile water. And you know, we start our day in our laboratories either by preparing distilled water, and this distilled water is used to prepare buffers or to prepare media. But sometimes you need to go deeper, and you need to go for deionized double distilled water or sterile deionized double distilled water, or sometimes you need to have this water even nucleic acid free. And all this high quality molecular biology grade water or sterile water is dependent on membrane technologies. Well, sometimes it's about desalting, deionization. So you go deeper in try to prepare media for cell culture for mammalian cells. In there, you need a variety of filters, membrane filters that are either dependent or polyvinylidene fluoride or polyether sulfone membranes. And you can use this either as a syringe filter or the cup filter. So early in the 1979, or in the last century actually, well, people intended to concentrate viruses or source of viruses before detecting the viruses by different chromatographic approaches that are dependent on membranes. And then, but recently, upon the outbreak of the SARS-CoV-2 that causes the COVID-19 disease, well, people optimized high throughput immune plaque assay for detection, for immune detection of the virus that is also dependent on nylon membranes or nitrocellulose membranes. And this is the detection outcome, the readout of the assay. In the dots you see on every circle represent a plaque which is representing infected cells by the virus. In the red color, if you immunostain with adequate antibody for the virus, instead of having a plaque that does not really tell you which virus it is, you use a specific antibody and you detect the virus on the membrane. So now we go deeper for molecular biology applications. If you wanted to detect proteins of the virus, or you purify recombinant proteins of the SARS-CoV-2 virus to raise antibodies against it, or to use it as a recombinant vaccine. So use it as a recombinant antigen for diagnosis or as a recombinant vaccine for immunization. Here you need some pre or upstream desalting using desalting columns, which are also dependent on desalting membranes. In these desalting columns, where you bind protein, you wash, and then you elute. And this does not only, usually these are ion exchange columns, and depending on the overall charge on the recombinant protein of the virus. In adding a graphite to the matrix, highly improve the downstream proteomics analysis. And then you have a protein cut-off filters that isolate particular, or enable you to isolate particular molecular weights of proteins. And this is a range of many or midi or maxi prep columns for purification of proteins of different molecular weights. And these are also dependent on membranes of 13 cutoffs. So you see, from distilled water to concentration of viruses, to detection of viruses, to isolation and purification of viral proteins, all dependent on membrane technologies. And then for proteomic analysis, where you isolate the proteins of any organism or any cell, or here in the infected cells or the virus, by either one-dimensional or two-dimensional electrophoresis, followed by Western blot analysis. So you electrically transfer the proteins from gels into nylon or nitrocellulose membranes. So the left-hand side would show you the 1D Western blot, and the right-hand side would show you the 2D electrophoresis on nylon membranes, where you see every dot here is corresponding to one single peptide. And then you elute these peptides, and then you determine the N-terminal amino acid sequence, and it tells you what kinds of proteins are either related to the virus or upregulated or downregulated in the cells upon infection. And all this are very important in the nowadays diagnostics. So you go to now nucleic acid detection, southern or northern blot analysis. You transfer nucleic acids from agarose gels into to nylon membranes, and then you detect either by autoradiography on X-ray films later on, or you probe so so these are a variety of membrane-based columns for mini, midi, and maxi prep purification of nucleic acids. Is a 96-well format of the high throughput isolation of nucleic acid, RNA, or DNA. So the strategy is lysis binding of nucleic acids to columns, desalting, washing, and then elution, and then precipitation if you need to further concentrate. So the nanopore sequencing technology, which enables you to do whole genome analysis or whole genome sequencing, is also based on graphene membranes or silicon oxide or silicon nitride. And it really gives an opportunity to sequence a whole genome of an organism. And this is the development of genomics of the nowadays. So if you wanted to go for reference genome analysis of any creature, you can use this. They are improving now the quality of the reads so that you don't get a lot of mismatches. But however, without the membrane technologies, you cannot do that. So now I can share you some of the collaborative work that we did in collaboration with the Flat Sheet Membrane Group at the Central Laboratories Network and the Centers of Excellence, where we try to address an issue which costs the National Research Center a lot of money every day. And this is simply the fact that with the fancy deionization or double distillation equipments or pyrogen-free water preparation equipments that we use in every laboratories at the NRC, we need to exchange the matrix and sometimes exchange the columns. And we need to pre-clean the water ahead of the passing the water through the column system to make sure that it would not be clogged. And all this costs a lot of spare. And what the Flat Sheet Membrane Group actually did is that they developed or they tailored a gradient water purification system. And then we compared the quality of the inlet water, the midstream and the downstream water with the water that is provided with the reagent, the molecular biology reagent kits, so-called molecular grade waters. And if you see this is a protein, agarose gel electrophoresis for DNA ladder. The first lane on the left-hand side here where the cursor is showing, it shows the resolution of the nucleic acid marker ladder on the fed water to ahead of the cleaning or the water purification. The second lane is corresponding to the molecular biology grade water used to prepare the reagent buffers. In the last lane on the right-hand side represent the one where all reagents and the gels were prepared by the water, the outlet water that is prepared through the gradient water purification system done by the Flat Sheet Membrane Group. And you see that the quality and the sharpness and the resolution of the DNA marker bands is quite comparable with the molecular biology grade water. And you see that the quality is different from the fed water. So the good news is that we have a system that is homemade by the Flat Sheet Membrane Group that gives us a good quality water comparable to the molecular biology grade water that needs a lot of money to be prepared or to be imported. So then what we did later on is that we did PCR reaction using the water that is outlet that is coming from the gradient water purification system, which was tailored by the Flat Sheet Membrane Group. And this is the sharpness of the PCR product band corresponding to where the reagents used were prepared by our water. In the first lane next to the marker is representing the fed water, the untreated water, in the last lane here, corresponding to the molecular biology grade water, and you see that the molecular, the water outlet or the downstream coming water from the system, the water treatment gradient system that is done by the flat sheet membrane group, gives the best quality of in terms of sharpness and the intensity of the PCR product. So now go to the effect of, or the, if we use the downstream water coming from this gradient water purification system to use to prepare media, to use it in preparation of liquid culture of bacteria. Here, the case is for Streptococcus pneumonia. You see that the best growth was obtained by our filter. And the same holds true for Staph aureus. So the conclusion and the take-home messages that I wanted to leave with, although I am not a flat sheet membrane scientist, but I am application user, membranes has major applications in biotechnology research. Building bridges between material scientists, biotechnologists is a must to improve and add on such applications. This can lead to developing spin-off companies, which are highly welcomed at the political level in Egypt. Any products in this direction can be absorbed by the Egyptian biotech market. And this is what we are really working hard together with the team of the flat sheet membrane. At the end of my presentation, I would like to thank the people in my research group who did the majority of the molecular biology and the microbiology work. And I thank all the team of the flat sheet membranes for their fine collaboration. And thank you for your attention.
Thank you, Professor Mahmoud, for his nice presentation. We will move now to the next presenter, Professor Heba Abdallah, team member of our project and a very active member in the flat sheet membrane group. She will present now in the title of the project development of spiral wound modules and the effect of working with PVA layer on the resistance of layer.
Hi everybody. I'm Professor Heba Abdallah, Professor of Chemical Engineering in Energy and Renewable Energy Institute, the National Research Center. I will talk the task 2 in the project of development of spiral wound modules. The BI, you know, Professor Dr. Marwa Shalabi. The task will be effect of coating polyvinyl alcohol layer on the resistance of membrane polyamide layer to chlorine. First, I will talk about the fouling. About membrane fouling. As we know, we have 4 common types of fouling: colloidal fouling, where the dust and rust parasites and particles can precipitate on the membrane surface. Protein, and the second one is organic fouling, where proteins or organic compounds can precipitate on the membrane surface. Scaling fouling is a third type, where the divalent and trivalent ions like calcium carbonate, calcium sulfate, and others ions can precipitate also on the surface of membrane. Fourth one is the biofouling, where the membrane biological fouling here can result from aerobic bacteria, which found in brackish water or seawater, or wastewater, or anaerobic bacteria which found in groundwater. Actually, the colloidal fouling and organic fouling mostly found in microfiltration membranes and ultrafiltration membranes, and these fouling can be removed by backwash for these membranes. Where the scaling scaling fouling and biofilms or biofouling mostly occur in nanofiltration membranes and reverse osmosis membrane, and these need chemicals to treat these fouling. Membrane biofouling. One of the greatest problems of the RO membrane is the biofouling. It is a reversible adhesion of microorganisms on the membrane. These adhesions involve 3 steps: bacterial adhesion, which can become irreversible in just hours; microcolony formation; biofilm maturation protects the bacteria from biocides, flow shear, and predators. What is the surface of the membrane which favor adhesion of these bacteria or biofilm? When the surface of membrane was rough, it can be more or it favor the adhesion of the bacteria. Surface charge, the neutral or positive surface, also means a more adhesion of bacteria, where this bacteria mostly negative charge. Hydrophobicity, the more hydrophobic membrane means more adhesion. But pre-treatment for the RO or before the RO means the biofouling can appear. The mechanism of the biofilm, first, the solution, if this of the feeding solution contains any proteins or nutrients, it will be a formation of conditioning adhesion. Second, physical and specific interaction between bacteria and surface leading to irreversible adhesion. Third, the adhesion and co-adhesion of bacteria leading to growth and metabolism by adherent bacteria. The techniques to overcome this biofouling. The objectives of the biofouling treatment method mostly to kill these microbes or remove or dead these microbes' bodies, prevent adhesion, propagation, and biofilm maturation, remove nutrients that foster microbial growth. What is these techniques? These techniques may be prevention of bacterium or organic neutral source, membrane surface modification, disinfection, or sterilization of the microbes. Removal or prevention of the bacterium. There is 2 types. Physical disinfection technique. Using UV can prevent or can hinder the reproduction of bacteria. Using membrane technology like microfiltration and ultrafiltration as pre-treatment units before RO also can remove bacteria according to the particle size. A second type, chemical disinfection techniques, which means I use some chemicals like sodium hypochlorite, sodium dichloroisocyanurate, or others to make a disinfection for the water before RO. Another technique is a membrane surface modification. 3 kinds or 3 ways to make a surface modification. Reduction of rough surface by coating of hydrophilic polymers like polyethylenamine, polyacrylic acid, polyvinyl alcohol. Second method, blending polymers using antimicrobial nanoparticles such as silver, titanium dioxide, zinc oxide, and carbon nanotubes. Third one is a grafting method by polymerization technique or by free radical technique, which mostly contain 3 steps: initiation, polymerization, and activation to make an active site on the surface of the membrane. Actually, in these steps, we have 3 granted patents in blending technique, and we have submitted 4 patents in the surface modification and blending techniques also. About this, the task in this project, this task objectives is development of the thin film composite membrane selective layer by coating technique using hydrophilic polymer and metal oxide nanoparticles to enhance membrane hydrophilicity, resistivity to chlorine, and enhance antifoul properties of the membrane. Actually, we have three types of membranes: commercial one, M31, and this commercial one was treated or have we actually made a coating by polyvinyl alcohol and cross-linking by glyceraldehyde. And M32 is the treated membrane surface using also a polyvinyl alcohol with zinc oxide and cross-linked finally by glyceraldehyde. Other three membranes related to the first three membranes, M34 and 35 and 36, just depends on I used these membranes and I soaked them in sodium hypochlorite for 24 hours. Scan electron microscope for the prepared membranes indicate that M31, which hasn't no coating, the thin film of polyamide layer appeared like on the surface, as you see, like leaves of tree. M33 and M32, this leaves is disappeared due to coating by PVA layer. The membrane performance test, we studied effect of free chlorine on different membrane activities, effect of chlorine concentration with synthetic salt solutions, and fouling test by sodium alginate. First, the effect of chlorine on different membrane. Fouling test scheme, we use sodium alginate as a model foulant. First one, with the distilled water was permeated through membrane for 5 hours. Second one, sodium alginate solution was permeated through 5 hours. And finally, the distilled water was passed again for 5 hours. We calculate flux recovery ratio and reversible resistance. And conclusion, biofilm is the greatest problem of the RO membrane. Different methods can be used to overcome the biofilm problem, surface modification, coating by PVA and PVA zinc oxide developed thin film membrane surface hydrophilicity. The membrane performance enhanced after coating by polyvinyl alcohol and zinc oxide. The effect of chlorine on the modified membrane was studied using chlorine in the feed solution led to increase in the permeability and reduction in the rejection, but using PVA coating layer alone and with zinc oxide withstanding and resist chlorine attack. Surface modification of membranes using polyvinyl alcohol and glyceraldehyde in the presence of zinc oxide nanoparticles shows the better anti-fouling behavior. Thank you.
Thank you, Dr. Heba, for your nice presentation. We will now present our next speaker.
Mara, sorry, can I have a question, please? Can I ask something?
Yeah.
So I just wonder, so first of all, good morning, everybody. Heba, you mentioned, and I think Mara, you too, you mentioned the deterioration of these membranes by chlorine-containing feed solution.
Yeah.
Are you typically using such a chlorine-containing feeding solution, or do you use, for example, brackish water or whatever?
Excuse me, Heba, you will reply? Or
we just using we cut the commercial membranes, and there is a two experiments. One, soaking these membranes on the chlorine solution, and the second is using the chlorine in the feeding solution in the experimental testing unit. Okay.
Okay, thank you.
Then we'll now present our next speaker. Excuse me. The presentation will be by Christoph. Yes, this is correct.
To be honest, I will start, make the first section, and the second section is done by Christoph.
Yeah. The next presenter will be Professor Ralf Polken, the German PI for our project. You are welcome. The floor is now yours. Thank you.
Okay, thanks a lot. And I'll try to give you my presentation here. Okay. So first of all, I'd like to ask Abdel Fayez to mute the microphone so everybody has the chance to have a good quality. Yeah. All right. So I'm just trying to get an idea about the questions. All right. So first of all, I'd like to invite myself just a short moment. So my name is Ralf Wilken and I come from the Fraunhofer Institute situated in Bremen. We are dealing with applied materials. For example, you see here our nice institute, and I'll go to the next slide. Hopefully you can see all the slides, yeah? Christoph, sieht man, ne?
Yeah, I see them.
Okay. So firstly, about the Fraunhofer Society. So this is the head of our organization. So we deal with the applied research, have about 74 institutes and research units spread all over Germany. And about 28,000 people are there working with the applied research. And we've got a total annual budget of about 2.8 billion euros. And what's very important is that about 70% is generated through contract research, either by industrial research or publicly funded research projects. So the positioning of the Fraunhofer Society is between the universities and the industry. So we are typically using basic research results from universities and bringing them into industrial applications. So this is our main mission of the Fraunhofer Society. So here's a short map of Germany, and you'll see Fraunhofer IFAM was founded in 1968, and right now we've got quite a lot of locations. So our main site is situated near to the Northern Sea. I hope you can see my my mouse, yeah. And you see that we also have some subsidiaries, one in Oldenburg, in Stade, so that's nearby Airbus, Wolfsburg and Braunschweig. This is near by the site from Volkswagen. We've got also another subsidiary in Dresden and also one in Helgoland, which is a very tiny island in the Northern Sea. So Fraunhofer IFAM has about 690 employees and a total budget of about 60 million euros. And the core competencies of the Fraunhofer IFAM are typically surface technologies and adhesive bonding. So these are the two main core competencies Christoph and me we are dealing with. We are also dealing with the polymeric materials, and we also bring these surface and adhesive bonding technologies to huge structures. For example, you can see here a big vessel from aeronautics. So this is the typical automation and digitalization. And another core competencies are shaping and functionalization. So, for example, we are dealing with the casting technologies, we're dealing with electromobility, and also with metallic materials, powder metallurgy, for example. But the main core competencies which are also asked in our project is surface technology, maybe a little bit of adhesive bonding. So I'm the head of the department Plasma Technology and Surfaces, and we have the following technologies in-house. So we are dealing with low pressure plasmas, ambient pressure plasma, also vacuum UV technology, as well as laser technologies. We are also dealing with plasma, with blasting technologies, and also some grinding and brushing. So these technologies are used for pre-treatment prior to bonding or coating or painting. And typically, we are specialists in the control of adhesion and dehesion, but also the control of wetting and de-wetting, let's say. So maybe a short introduction about the basics of the plasma technology. So you can see here a typical gas, and if you put in a little bit energy into this gas, you can excite this gas, for example, by electrical fields. So typically we are using radio frequency, sometimes also microwaves are used for the ignition. So then we have got not only the gas molecules, but also excited molecules inside the plasma. But we also have some radiation. So there's also vacuum ultraviolet radiation, for example, but also IR radiation. So everything in between. And there are also some molecular fragments which are highly energetic. So these are very excited species there. And last but not least, and this is the main issue of the plasma, that you also have some free electrons and some ions inside this plasma. So all these species, so typical gas molecules, excited species, also radiation and ion and free electrons are inside the plasma. So what can we do with such a plasma? For example, if we use oxygen molecules, we end up with these excited states and many others. So these are excited ions, excited radicals, atomic oxygen, and so on. And all these excited species can be used to remove, for example, organic contamination from a substrate. So please imagine that you've got maybe here a metallic substrate, and you have maybe a slightly contaminated surface with organics. You can use only these plasma species, which are burned cold, let's say. It's a kind of cold burning. And you remove all these organic contamination and end up with a very pure and pure surface of the substrate. But you can also use a polymeric substrate, which is maybe not contaminated, but has also organics on the surface for sure. And also, if you use these oxygen species from the plasma, you also end up with oxygen containing functional groups on the surface. So you've got a kind of surface functionalization. And this can be seen here, for example. So we've got two XPS spectra. So the dashed line of the spectrum. So that's a typical low density polyethylene. So it's only one peak, nearby 285 electron volts binding energy. So this is really aliphatic carbon, which is very typical for LDPE, and there's only a very tiny shoulder here at higher energies, binding energies, and it ends up with a quite pure surface. About 98% of atomic percent is carbon here at the LDPE surface. If it comes to a plasma treatment, for example, by atmospheric pressure, then we'll get this second spectrum, which can be seen here. So we've got some shoulders here, and these shoulders are assigned for, in this case, for example, ethers and also alcohols. Here we've got some carbonyl functionalities, but also here some carboxy functionalities. So esters, but also carbon acids, for example. So, and by the incorporation of these oxygen functionalities, we also can increase the surface energy of this surface of this LDPE. If we use then such a technology for the pre-treatment of surface, and we do some adhesive bonding tests, for example, as you can see here, so a typical Lepsche test, which is seen here. So here's the adhesive. In our case, it's a polyurethane and these two polymer substrates. You can see that in every case, if you use different polymers, you can really increase the Lepsche strength by factors, let's say. So also the failure is changing from, the failure mode is changing from adhesive. So also in this case, so the pristine is very little, has very little strength. And so here we've got an adhesive failure mode. And after the AP plasma, you can see that it switches to a cohesive failure mode and gives very high Lepsche strength. So this is because of the increase of wettability, but also increase of the surface reactivity. So how do such plasma devices look like? So there are two main different kinds. So it's the so-called low pressure plasma device. You're typically using a plasma reactor and also an RF electrode where you can put in some energy inside this gas phase. And you also need a gas supply system and also a vacuum generation system here. And this is, for example, quite a big machine in our lab. So this is a typical plasma reactor. In this case, it's about 2.5 meters long, 2.5 meters high, and about 2 meters wide. So a quite big machine. And it allows, for example, the treatment of wet materials. So this is, for example, the ideal machine if it comes to membranes or whatever. The second method we are using for the ignition of plasmas is the atmospheric pressure plasma. In this case, it's a jet system. What we use here is a nozzle kind system where we ignite a discharge from this inner electrode to this housing. And by applying, let's say, a working gas here, the plasma comes out of this nozzle and gives, in this case, a good plasma effect. And if, for example, you apply also some monomers, you can also apply plasma polymeric coatings on the surface. So that's something we, for example, use also in automotive industry if it comes to such a aluminum die cast housings. And you can also combine this with robot techniques, so it's ideal for inline processes. In case of low pressure plasmas, it's more or less a batch process. Last but not least, and this is the main technology we are using in our project, is the vacuum ultraviolet excimer technology. So what we do here is that we ignite a plasma inside a lamp. So it's more or less the electric barrier discharge, a DBD system. And in this plasma, we change, so it's filled with xenon gas. And this xenon gas is excited and forms, let's say, this dimer. So it's an excited dimer. Excited dimer, the short version is excimer. Yeah? So excited dimer gives excimer. And this is this forms again two xenon atoms, but also a very nice photon with wavelength of about 172 nanometers. So it's very energetic, and it's in the range of vacuum ultraviolet radiation. So it's below 200 nanometers wavelength. And the advantage of this technology is that about 95% of the light goes into VOV emission, and therefore it has a very high efficiency, this technology. And we can also use this technology for surface activation of polymers. You can see, for example, here the spectrum, the spectrum of the polyethylene in the vacuum ultraviolet radiation. And you can see that you have an overlap of this spectrum of the lamp, so this excimer lamp, and this polyethylene spectrum. So in this case, in this area, we have an absorption of the light. And this gives you quite a lot of functional groups, as I mentioned also before, in the case of plasma technologies. We also form, for example, esters, carboxyl groups, carbonyl groups, and also ethers, and so on. And the effects are a little different. So we have the typical photooxidation. So that's the combination of oxygen and the photons, the vacuum ultraviolet radiation. So this changes the surface, but you can also have just a pure oxidation, because the radiation and the oxygen forms also ozone and also atomar oxygen, which also changes and alters the surface. And the big advantage is that from this vacuum ultraviolet radiation is that you also change the subsurface. So the radiation can propagate, let's say, some 10 nanometers into the surface. So we've also a change in the subsurface. And this gives a very high stability of all these nice effects. And it's also maybe interesting if it comes to the treatment of membranes, RO membranes. So next slide is the adhesion behavior. The adhesion behavior of these pre-treated surfaces you can see here. So in this case, we did a 180 degrees peel test, and we looked at the peel resistance in case of an unchanged pristine material. We've got nearly a direct failure. So the value is very, very little in all cases. And if it comes to vacuum ultraviolet radiated and activated surfaces and do the same peel test, we end up with very high peel resistances. So this gives you, again, a feeling of this prominent effect. So that's how these systems look like. So it's more or less a typical lamp, but you have to make sure that that you have an exhaust system, because ozone is formed during the treatment. And now I would like to hand over to Christoph, and hopefully he can switch on his microphone right now.
Yes, I do. Hello from my side. I hope everybody can hear me.
Yes.
My name is Christoph Schmiezer. I'm a chemical engineer, and I work also at the Fraunhofer Institute for 12 years. Yeah, 12 years. Yeah, let me give you a short look about our project. It's called okay. The title, Development of Spiral Wound Modules for Cost-Effective and Long-Term Stable Desalination by Anti-Fouling Coatings on Membranes. Okay. Yeah, our motivation is we do investigations on long-term stable hydrophilic anti-fouling coatings based on vacuum UV treatment. And here on the left side is a spiral wound element showed, and I show it to that you can see that we are dealing in this part with the feed water carrier. In the following slides, I call it a spacer. We activate this spacer. And also we're dealing with the semi-permeable membrane. This here is a close-up picture from this polyether sulfone membrane. Yeah. Okay. Here's the. Yeah, we can go to the next slide. Thank you. Here are a look inside our activation and coating plant. Here we can do the activation of the spacer or the PES material. On the left picture, there is the spacer fixed on our table, which table can move under our VOV lamps. And can you click twice? And one more time, we have a close picture from the spacer. Here we see with a mesh structure. Okay. Also, we have on the right picture, we have the VOV activation. And the close-up picture here is the PES membrane. Okay, you can skip. Here are pictures from our plant. We have here this plant we use for our treatment from the red material. We can see here the winding system where we have the wet material on. And we have in this plant we have different units. In this I show here. No, nobody can see my cursor. We have a VOV unit where we can activate and irradiate our wet material. And in front of this, we have a coating system where we can coat something on our wet material. And yeah, that's our plant. Okay, okay, that's thank you for your attention. And yeah.
All right, so I'll try to hand over again.
Yeah. You will have another talk, Ralph?
No, that's it.
Yeah, you have.
Okay. Now you can take over the control again.
Yeah, sure. You have the floor now.
So are there maybe some questions you can answer?
Okay. If there are any questions? If there are any questions? Yeah. No question, but I have only one question. Excuse me. During the presentation of Christoph, he was spotting winding and winding of a sheet. This means that you are treating long sheets, continuous sheets in your setup.
So right now we are able to, but right now we've got only very little samples from you, and therefore we use the transfer unit, but not the winding unit.
Yeah.
But it gives similar results.
Yeah, I see. Thank you. Is there any questions? Yeah, no questions. You have any comments, Ralph?
No, not yet. So first, or maybe one. First of all, thank you for the invitation and giving me the opportunity to present here in this nice community. And thanks for all. Yeah.
You're welcome.
Thank you.
Thank you. Finally, I want to thank all the presenters. Thank our colleagues from Germany, our partners who are sharing us the findings and the achievements in our work, and hoping to get in the next year, because we are now finishing the first year of our working schedule. So hoping the next year we get the whole targets, which was our aims in the beginning of the project. So hope to see you all the participants and many others in the next year by the second and the final workshop, giving a whole presentations and a whole view for our achievements and our findings. Also, I want to thank my professor, Professor Ahmed Shaban, the head of my group and the copy eye of my projects, for his continuous effort for supporting us as a group. Also, many thanks to my colleague Heba and Professor Bahgat for their presentation today, and hoping you all to be interested in our meeting. Finally, I want to say, because I have many comments on the chatting room, for the summary for our workshop, not the whole presentations, a summary will be a collective summary for our presentations, will be collected and put on the YouTube channel of our group.
Perfect, Mara. And maybe one more little amendment or one thing to say. So hopefully we'll see us next year directly, and that we can.
Physically, yeah.
Very good.
Hope so. Yeah. Thank you, and hoping you a fruitful and good day. Hoping you the best.
Okay. Thanks a lot.
And hoping you Merry Christmas and good New Year for all of us, with full of hopes and full of achievements.
Yeah, perfect.
Thank you.
Thank you.
Thank you. Bye.
Bye.
Thank you all attendants, all participants, and hoping to see you soon. Bye.